about to get a bird's eye view of the Sunshield. To tell us more about the Sunshield, which is actually made up of 5 layers of a material called Kapton, we have Andy Tao. He's the chief engineer for the Sunshield. Andy, tell us first of all, what is the Sunshield for?
Well, the Sunshield's main purpose is to keep the energy from the sun from getting to the telescope. JWEST looks for very faint, basically thermal objects out in space. It's important to keep things really cold. So if we were to allow the telescope to heat up, the warmth of the telescope itself would just swamp out the sensors and it wouldn't be able to see anything except its own heat. The second thing is just to keep out the visible light also. The visible light can get inside the optical train and cause all kinds of interference, so we want to keep that out too.
Now, Andy, I mentioned before it has 5 layers of a material called Kapton. Before I ask you why 5, what's Kapton?
Kapton is essentially a space-age plastic film material. It's something that's been developed for a number of years, and we actually use it in our thermal insulation materials.
Okay, and 5 layers, why is that?
5 layers, well, 6 would be too many and 4 would be too few.
You've got this down.
Yeah, well, it actually has to do with the amount of energy that we need to reject from the sun. The sun is putting in a certain amount of energy, and we need to reject that and make sure it doesn't get to the telescope. The Sunshield is built so that there's an angle between each one of the layers, so heat that comes off of layer 1 gets bounced out and actually gets rejected out the sides. So if the spacecraft was down here, we actually have a couple of holes in the Sunshield that allow heat to come up from the spacecraft and get pumped out through the sides. So the Sunshield is sort of like a giant heat pump, passive heat pump.
This is not the flight hardware, right? This is actually just a test article.
That's right. This is one of our series of development articles, and a very important one. It's full size, and it's pretty close to flight, but there's some important differences. All right, ready to come down? Coming down.
Oh boy.
These layers that you see right now actually will be coated with a vapor deposited aluminum.
Okay.
And that aluminum, which you see here on the underside of the thermal covers, is 99.99% reflective. So that helps a lot when we're trying to bounce all that thermal energy out of the Sunshield.
Okay.
Now the kind of pinkish purplish part is actually a silicon layer.
And that's the one that's exposed to the sun?
That's right. But we use the aluminum, the super highly reflected aluminum, everywhere else that we can to reject the heat.
Great. Thanks a lot. This silicon layer actually protects the Sunshield during launch. And when the James Webb Space Telescope Observatory reaches its destination 1 million miles from Earth, this silicone cover gets deployed. Thanks for joining us for another edition of Behind the Web.
In a city that sees a never-ending stream of visitors each day, it takes a lot for any newcomer to stand out. But then, this visitor is no ordinary guest.
You know, I imagined it, but I never thought it would be this big. It's spectacular.
Spectacular is this life-sized model of the successor to NASA's Hubble Space Telescope. Its home, temporarily, is New York City's Battery Park.
When I first came in and I saw it, I thought it was a beehive because of the mirrors, how it looks in the colors.
Not exactly a beehive, but an attention grabber nonetheless.
What brings the model of the James Webb Space Telescope to the Big Apple is the World Science Festival. Nearly a week of science learning, not in the classrooms, but on the streets of New York.
If we can get kids excited about science, that's fantastic. And if we get their parents excited, that's even better, because that they then help bring their kids to these kinds of events.
Here, people have a unique chance to get up close and personal with a telescope that looks like no other before it.
You've got to consider things differently when you want to put things in space, and that may end up looking very weird on Earth.
It's nice how the kids and adults and parents see what it really looks like, even though it's a model.
Sure, it's only a model, but it's also a great tool to show what's in the not-too-distant future.
It's wonderful. Many tourists coming to New York, so it's a great exposure for the program.
Just getting to know a little bit more about science and a little bit about the new innovations around you is really important.
I'm glad to see that there's still progress being made and big projects being undertaken.
A bold project to extend our future vision to the farthest frontiers
James Webb
of the
Space
universe.
Telescope will be 1,000,000 miles from Earth. Right now, there are no plans for astronauts to actually go and fix it. So what happens if something goes wrong? So what exactly are you folks doing right now to make sure that the James Webb does work properly?
Okay, the electronics that we build are an advanced version of the actual electronics that will be on the spacecraft. So we actually test them on the ground before they launch, so that once we launch, we can actually simulate any problem that might happen once the spacecraft is actually deployed in space.
So a simulator like a game simulator?
Yeah, it's actually a lot like a game simulator, maybe with not as much visuals as you're used to, but we actually have a lot of data that will be floating by on the screen that indicates things like the temperature of the spacecraft, what direction it's pointing, whether antennas are communicating back and forth to Earth, things like that. The electronics that we will be testing actually is located underneath in the spacecraft compartment there, and that is responsible for sending all the data down to Earth and back up to Earth, controlling the satellite.
Hi, Alicia. So what are you doing here?
I am looking at data from a simulated spacecraft of the observatory. So this is our system, our ground system that we use to look at telemetry, send commands to the actual vehicle, and do our real-time assessment of its health and safety.
So basically, in a nutshell, it's like you're getting the pulse or the vital signs for the instrument.
Absolutely, absolutely. This pretty much is our eyes into what's going on the satellite, and we determine by looking at all of this information, are we safe, and what do we need to do to get us safe.
So as you can see, a lot of work is being done right now to make sure engineers on the ground keep the James Webb Space Telescope up and running throughout its lifetime.